The third and final bridge that I really don't want to cross with this project assumes that we have failed in both Plan A and Plan B, and at that point, we're just going to take the battery out and recharge some electric eels with it, and then just enjoy the weight savings and run just on the 13B. I've been talking about making this rotary swap a functional plug-in hybrid, but I haven't really talked about how we're going to go about doing that. There's a couple different approaches, the first of which is going to play nice with all the factory electronics, and that's the path we're going to try to go down first. There's a fallback option B, and then if all that fails, then there's a last final option that hopefully we won't have to get to. So like any modern BMW, the i8 has way too many communication buses. There's like 7 different CAN buses, a bunch of LIN buses, and then there's also FlexRay. If you're not familiar with FlexRay, it was kind of a blip on the radar in the mid-2010s of German auto manufacturers, and it's kind of fallen out of favor for more modern or faster communication buses that have taken over. Think of FlexRay as sort of like a CAN bus on steroids. With CAN, you have a bunch of modules all connected, and they're all spewing data onto the bus, and through message ID arbitration and filters and everything, all the messages get to where they have to go. FlexRay is also a distributed bus with a bunch of different modules on it, but instead of all the modules just spewing data onto the bus, each module has a very specific window in time in which it can communicate its data. So the whole system is kind of self-regulating. There's no clock, and all the messages have to be sent within their specific time window, otherwise you'll have an error. With CAN bus, it's easy to put a man-in-the-middle type box in there to intercept messages, alter the data, and then send that back out on the bus to achieve a manipulated result for whatever sort of motor swap or control that you're trying to do. Unfortunately, with FlexRay, it is time deterministic and extremely difficult to intercept a message, alter it, and send it back on the bus in such a way that it's not going to cause a fault. Not only do we have this irritating data bus that we can't easily manipulate, it's also tied into all of the critical powertrain components. So the internal combustion ECU, the starter generator that's attached to the engine, and the EV drive up front is all connected to the FlexRay bus as well as the power steering system. Having come to terms with the fact that the FlexRay is going to need to remain intact and functional to have the best integration that we can possibly get, we are going to keep the factory DME for the internal combustion engine in the car. We're going to have an intermediate controller that is going to feed that enough signals to make it think that there's an engine attached, and we're going to feed that controller with the CAN bus signals from our ECU Masters Pro 16, so it has the actual real data of the temperature, RPM, all that fun stuff. Now, anybody that's done any series level of tuning on a modern torque-based ECU is probably falling out of their chair laughing at the idea of making it think that there is an engine attached to it in a reasonably functional manner. But the reality is that we only need to coax the factory ECU into going into a limp mode just enough to get the system to come online and get everything else to run. So my go no-go as to whether this could actually even work was to unplug most of the factory ECU, leaving just the power and FlexRay in place, and powered up the car, and obviously all sorts of drivetrain codes, but it would still drive in EV mode. So we put the car into a condition where it would in no shape or form start the internal combustion motor, but it would still drive in EV mode, the power steering still worked, and everything would move. At that point, I was reasonably convinced that I could make this work. One of the other nice things about having a fault-tolerant modern system is all the diagnostic codes that it'll spit out at you when you put it into that sort of condition. So it becomes a game of fault code whack-a-mole to address the most critical ones to get the car closer and closer to a state of reasonable functionality. Now, in communicating with the factory DME, it's one thing to feed it with all of the signals that it wants to see, but we're also still going to have to dive inside of that and do some factory ECU tuning. So the idea is to go into the factory DME file and find some of the fault thresholds and then max those things out so it makes it less likely to throw the ECU into an error state. Ideally, we'll have the ability to suppress some of these errors too and get us to a better state of functionality. So the critical part to making all this work is going to be the custom controller that resides between the factory DME and the ECU Master Standalone, and that's where today's sponsor, JLC PCB, and their sister company, JLC 3DP, come in. Just like the name suggests, JLC PCB is a manufacturer of custom printed circuit boards and printed circuit board assemblies with all the components turnkey ready to go. And their sister company, JLC 3DP, offers 3D printed parts in materials such as various resins, SLS nylon, MJF nylon, even stainless steel. I've been using JLC for about 4 years now on a variety of different projects, and they've always been fast, cheap, and good, which is a pretty rare trifecta to find. My most recent project was a USB to LIN bus interface, and I had the PCB done as well as the 3D printed enclosure. So check out the links to JLC PCB and JLC 3DP for your custom PCB and 3D printed enclosure needs. It's definitely not as advanced and scary as it might seem to develop some really effective controllers for automotive use, and you definitely don't need an electrical engineering degree for a lot of this stuff, so I'll show you how to get started on that in a future video, but let's get back to the hybrid system today. The foundation for our custom intermediate controller is going to be this TE connectivity header. It's 154 pin count, and it has two IP67 sealed connectors. It's actually an OEM part number for a bunch of Magneti Marelli ECUs, and at least visually it's probably used on a bunch of Bosch ECUs as well. It's actually kind of challenging to find a pin header that has a count this high, as well as a mix of both power and signal pins, but this was the most reasonable, attainable part that I could find, and is regularly stocked at DigiKey and Mouser from what I've seen. You can buy a knockoff of this with an aluminum housing on Ali eventually, but anything for critical signals, I like to use actual OEM parts wherever possible. One of the first parts that we're going to source from JLC PCB on this project is going to be the housing for this header, as well as a bare PCB blank that we're going to use just as a design reference while we're working through the layout of the schematic. One of the problems that I have when I'm designing electronics is that I quickly lose a frame of scale reference, and I find it really helpful to have a PCB that's the outline of what you're actually trying to design to. It's just helpful for laying things out and getting an idea of scale and how much space something's going to take up. On top of that, a custom PCB alone is like $2 to $5, so it's a very valid investment. So on top of all the digital and analog signals that this controller is going to have to replicate, it's also going to have 3 different CAN buses, as well as a couple LIN buses as well. 2 of those CAN buses are going to talk to the BMW Powertrain 1 and Powertrain 2 CAN buses, and then the third will be my own private CAN bus to send messages to a custom screen, custom controllers, anything else that I put on the car. And then things like the LIN bus will be able to control the speed of the CWA 400 water pump and other similar devices. Plan B would be a slightly more invasive approach where we replace the logic board inside the EV inverter up front with one from an open source group called Open Inverter. I used Open Inverter parts to control the Tesla large drive unit back in my E30, and even contributed a little bit to some of the firmware for drivability upgrades. The positive here is it has full control of the inverter, and we could definitely output way more power than the factory unit would be limited to. The downside is that the factory inverter also has the DC-DC converter. Think of this as an EV alternator. It takes the 400 volts out of the battery and then drops that down to 14 volts to power the rest of the 12 volt system. The other problem is that the battery charger itself and all that circuitry needs to communicate with the factory inverter, in which case it will be lost. So then I have to deal with adding a charger, a DC-DC converter, and then also deal with interfacing the BMS CAN bus with the rest of my own charging system. I realize that was more acronyms than a corporate strategic marketing presentation, but Google is your friend here, and you can find a lot of good information on the basics of this stuff, and I will cover some in more detail in future videos. The other issue with the open inverter approach is that we do lose our FlexRay, so we are permanently going to have FlexRay errors on the car, which is kind of annoying. The last challenge to Plan B is that the generator starter inverter in the rear of the car, I would need to either replace or figure out some sort of logic control on that, which would be a fun reverse engineering exercise in itself. And by fun, I mean grossly time consuming. However, the big upsides to Plan B would be some really crazy control stuff that you couldn't do otherwise, because you have full independent control of the EV system, as well as full independent control of the internal combustion engine. You could put the rear engine in forward, you could put the front engine in reverse, and you do some pretty sick donuts. The third and final bridge that I really don't want to cross with this project assumes that we have failed in both Plan A and Plan B, and at that point, we're just going to take the battery out and recharge some electric eels with it, and then just enjoy the weight savings and run just on the 13B. So while our failback option will still yield a lighter, faster car, it's just simply not going to be as cool and interesting as if we got the hybrid setup to work. The one thing we need to address as part of our control strategy is, because we're using a standalone, there's going to be multiple modes and settings and stuff that we could choose from, but you need switches and buttons in order to get there, and the way that the interior is laid out doesn't really offer a whole lot of good options for mounting like an aftermarket CAN bus keypad or anything like that, at least in such a way that's going to flow well with the interior and look good. I've already got my phone charger here that I don't really want to give up. I could put a CAN pad here, but then you run the risk of hitting with your elbow while you're perhaps doing some spirited driving. So one of the ways that we're going to deal with this is going to be twofold. It's going to give us some buttons and deal with this, which in the overarching history of BMW steering wheels. This is not the most terrible iteration out there, but it's a little big. I generally hate the blue theme that BMW went with on their I-Series. I actually went through great lengths to make sure that the car that I bought had the frozen gray exterior accents rather than the blue. You can probably also see right here where the leather is starting to shrink, or you have some adhesive or something starting to show through the leather. And that's not atypical of some of the interior quality that you're gonna find on this car. I'd be really disappointed if I spent 150 grand on this, but at the roughly $50,000 current market price, I could probably look past that. The other thing that we're eventually gonna do on the interior is build a custom LCD screen that's going to reside around here and integrate in such a way that flows with the dash. Let's take this thing off and see what we're going to replace it with.
If he dies, he dies.
Well, we got the super clicky flappy paddle steering wheel installed. We're not done just yet because this is going to be our main tactile interface to our standalone ECU and our own custom controller. We want to get the most functionality out of that as we can, and the way that this wheel works currently is that there is a PCB at the hub that communicates to the car. So what I'm going to do is create a daughter board to that to add a CAN bus to the system, because right now the steering wheel only communicates over LIN. Looking at the clock spring, there appears to be 3 unused pins, 2 of which I'd like to repurpose to pass CAN bus through the steering column. This way we can incorporate some sort of switching function in which under normal circumstances the wheel will pass the standard LIN messages for the cruise control and the media controls to the car, and then we can switch it out to be able to send CAN messages to our controllers and then do all sorts of fun stuff like boost control, traction control, different drive modes, all that kind of stuff. How we're going to go about setting up the EMU Pro 16 to handle all this is a video unto itself, but we're going to have more sensors than the space shuttle, which is probably fitting because we're definitely going to send some Apex seals into orbit. So if you made it this far, thanks for watching. As you've probably figured out, there is going to be a lot of nerdy ground to cover in terms of electronics, in tuning, and all sorts of integration stuff. So there's going to be a lot of content on that coming up. So hopefully you liked it, and we'll see you next time.